Dean with Gilson Engineering, and just cover ground rules before we get started here. I'm going to have everybody on mute during this presentation just because we have a large number of people in the webinar. If you have any specific questions, go ahead and type them into the chat box. Sean Gilson and a couple of folks from Gilson Engineering will be monitoring that chat box. They'll either answer you directly in the chat box, or when I stop for breaks, I'll go ahead and cover some of those questions. And besides that, this presentation will be for 1 PDH hour. So if you are a professional engineer and would like a Pdh credit, please send an email to me. I will show my email here in the next couple slides, and we'll make sure to get you a Pdh cert. With that, I appreciate everybody being with us this morning. I'm going to go ahead and get started. So just a quick background on me. Again, Ryan Dean with Gilson Engineering. I cover our Tampa territory for Gilson, and I've been with Gilson for 11 years now. I've worked in both applications and now outside sales for the past 10 years between the South Florida and Tampa territories. Once again, this presentation will be good for 1 Pdh credit. I apologize, it says on this slide Florida and PA. That's actually not true. If you're in Ohio, West Virginia, or Kentucky, it's also good for a credit. So go ahead and send me an email with your PE number and your contact information, and I will be able to, I'll be sure to get a cert over to you. So today's presentation is going to be specifically about ultrasonic and radar. We're going to talk about the two technologies, the pros and cons of both, and then we're going to dive into some applications. So the manufacturer that we represent is Siemens. This gives an idea of their entire product overview, but our focus today is specifically going to be on level and as it relates to continuous level for ultrasonic and radar. So one of the common questions that we get asked when we discuss level measurement is why do people want to measure level? There are a multitude of different reasons. Probably the two most common are going to be to protect from any sort of a spill out of a tank or out of a vessel. Some of those spills might be lead to fines for a potential customer or environmental cleanup. And then you'll also see people protecting equipment. So, you might not want a pump to run dry, for example, or you might be doing some sort of mixing or batching application, some type of a reaction. So many different reasons why we would want to measure level inside of a tank or a vessel. There are two different types of level measurement, point level and continuous level. The majority of our presentation today is going to be focused on continuous level. The main difference here is when we're doing point level, we simply tell you if the level inside of a vessel is above or below a certain point. So in this case, we have a point level switch installed horizontally into this vessel. If level were below that, we would have one state. If level were to go above that, we would change states. So it simply tells you level is above or below that point. Whereas continuous level tells you exactly how much is inside of your tank at any given time. And we typically correspond that to an analog 4 to 20 output. There are two different types of level technologies. There are contacting technologies and non-contacting technologies, and they're basically self-explanatory. A contacting technology is going to have some sort of a probe or a device that extends into the vessel and is going to come in contact with what's actually inside that vessel. So in this case, this device might be a guided wave radar, it might be a capacitance probe, and that probe is going to run the full length of your vessel, and as product comes up this probe, it's going to change your output, which will change your level reading. Versus your non-contact level measurement, that's going to be things like non-contact radar or non-contact ultrasonic, which we'll talk about today. One of the key advantages is you do not come in contact with the process in the tank. So you don't have to worry as much with things like material compatibility. How am I going to be affected by buildup, by corrosion, mechanical forces from the product coming in contact with probes. So Non-contact would typically be the preferred method when a contacting technology will work for your specific application. So one of the things that we're going to really focus on today is when we debate whether we should be using ultrasonic or radar as far as our technology of choice for measuring level is allowing the application to choose the technology for us. And the acronym that we use for that is STAMP. So we're going to look at the size of the tank or the vessel, the temperature and the pressure inside the tank or the vessel, what the media is that we're measuring, and then the atmosphere within that tank or that vessel. And these steps or these guidelines are really going to dictate for us which technology makes the most sense for your given application. So now we're going to jump into a little bit of a background on how these two technologies work. But before we do that, just a quick talk on ultrasonic versus radar over the course of time. So ultrasonic for the last few decades has been the more common or widely used technology. This slide says in water, wastewater, but throughout industry in general. And ultrasonic has always been the lower cost option between the two. And over time, radar has become more popular in use, and the price of radar has started to come down and be more competitive with ultrasonic. And we'll talk about that as we get more into this presentation.
Brian, when you say radar has become more popular, do you mean more popular than itself or more popular than radar?
Just the use of radar has increased significantly over time. So whereas ultrasonic, maybe used to be 75% of your applications, that radar has cut into that, and there might be closer to 60-40 or 50-50 out in the field these days. All right, so a quick explanation on how ultrasonic works. So what you're going to see with an ultrasonic transmitter is we have your transducer here mounted at the top of the tank. Let me back that up. We ping out an ultrasonic sound wave. It's going to go down. It's going to bounce off of liquid level in the tank, and it's going to come back up to your transducer. We measure the amount of time that takes to happen. We then divide that by 2, and that tells us how long it takes for that signal to go down to our liquid level. One of the things to keep in mind with ultrasonic is that we are looking for a change in density. So anything that has a different density than the air that the signal is traveling through will cause a reflection. We know what the speed of sound is through air. That's pre-programmed into that ultrasonic. So once we know how long it takes to go from the transducer down to liquid level, we're able to calculate a distance for you. And then based on how you have your ultrasonic set up, as far as the maximum range of that tank, we're going to take the overall range minus the distance, and we're going to calculate a level for you. So here's just a quick explanation or the math behind that. So your distance is simply velocity times time. Again, we know speed of sound through air. We know how long it took for that signal to travel from the transducer down to liquid level and back. That gives us our distance. We then divide distance by 2. That tells us our distance away from the transducer. Once again, based on how we have that ultrasonic set up to measure level, we'll subtract distance from overall span, and that will be the level in the tank. So the next slide I put up is just a quick overview of the product family that Siemens has for ultrasonic. So you see a couple of remote transmitters, an integral transmitter, and then our transducer offering. I'm not going to spend too much time talking specifically about the Siemens product line, but that's just an overview. So now if we switch gears to radar, one of the radar and the ultrasonic both work off time of flight measurement. So you're still taking a signal, you're sending it from the transducer, or in this case, the horn of the radar. It's going down, it's reflecting off the level in the tank, and it's coming back up. We're measuring the amount of time that takes to happen. there are two key differences here. The first is that that is a radar wave as opposed to an ultrasonic sound wave, which travels at the speed of light through whatever media is in here. It does not have to be air. And instead of looking for a change in density, we're looking for a change in dielectric. So any change in dielectric will reflect that signal up. Again, we measure the amount of time that it takes, divide that by 2. It tells us the distance, how far away we are from the liquid. Then we calculate your level based upon that. So 2 key takeaways. Ultrasonic is the speed of sound through air, and it's looking for a change in density. Radar is speed of light through any media, and you're looking for a change in dielectric. We'll talk more about how that relates to the way that these technologies work in the coming slides. And again, simply put a quick slide here that shows the different radar transmitters that we offer. So your traditional horned, Bluetooth style, solids radars, and guided wave. So again, I kind of already explained this, but once again, once you know the distance from the transducer down to your liquid level, we simply take the span that the transmitter is programmed for, we subtract out that distance, and that tells you the level inside of your tank or your vessel. That works the same with radar or ultrasonic. Some of the most common non-contacting level operations that you'll see, I think hands down the most common is going to be level. You might also see distance, which we've already talked about, from the face of the transducer down to liquid level. This is particularly beneficial when you're setting an instrument up. It might be much easier to put it in distance mode. Simply put a tape measure down into the vessel and make sure it's measuring the correct distance away from your liquid level. You can also use them for a volume calculation. If you know the dimensions of your tank, we take level, use a formula depending upon the shape of your tank, and give you a volume output. We'll see differential quite regularly, specifically if we're doing differential across a bar screen, like at the headworks of a wastewater plant. You want to know when that screen is getting clogged. We can do the differential on either side of the screen, bring that back into a single transmitter, and alarm or relay upon that value. And then you can also use ultrasonic or radar for open channel flow. And we'll talk a little bit more later in the presentation about why you would specifically want to use ultrasonic for an open channel flow application. All right, so at this point, I'll pause. Sean, do we have any questions that need to be addressed?
We do not have any questions, Ryan. I guess you're answering them all.
All right, that's a good start. So I'll go ahead and
Ryan?
Yes.
One just came in as I was saying that. He says, I've seen applications where the fluid in the tank becomes foamy, causing issues with understanding of the true liquid level. What technology, if any, would be best to overcome foam?
Sean, that is probably one of the biggest core parts of this presentation. I have multiple slides dedicated to that. If you don't mind, I'm gonna ask that you just hold off, and we'll talk about that specifically. It's a big part of the presentation here. Appreciate the question, though. You're hitting on exactly what I want you to think about. All right, so now we're going to talk a little bit about the digital echo processing between these two technologies, and they work very, very similarly. So this is what's going on in the background of either of these non-contact technologies while they're working for you or they're making the measurements for you. So what you're going to see here is a little chart. Along the y-axis here, I have decibels, which is basically the sound or the noise in the application, which we'll talk about in a moment. Along the x-axis, I have my distance. So on the left-hand side, I'm going to start at 0 distance from the transducer, and as I continue here along, that'll be the depth of my tank or my vessel. So my blue line here is the actual signal return, or the echo profile. that I'm seeing from the ultrasonic or the radar. So what happens is we'll send that signal out from the transducer up here, and it'll come down to some value. That value is what we call the noise floor. So every application is going to have some amount of ambient noise going on in the background. That's what this noise floor is. And then anytime you see a spike here, that's a signal return. So we're now reflecting off of something inside that tank or that vessel. This might be true liquid level, which is what it is in this specific application, but it could also be any sort of obstructions or anything that are in the vessel. And then my red line here is a threshold value. So in our case, with Siemens, that is a dynamic threshold. So it changes over time, and we'll talk about that a little bit more. But as process conditions change within your tank, this threshold might slide up or slide down as your signal returns get higher in amplitude or lower in amplitude. So as you have things like foam, for example, as Sean asked about, the foam in the tank is going to decrease this signal. So if the size of this amplitude comes down, that red line will come down with it. So we still continue to measure level for you, and we don't go into echo loss. That's the whole purpose behind having this dynamic threshold or the dynamic red line. So this kind of just talks a little bit about some of the things that I just mentioned. There's your echo profile, your varying threshold, your noise floor. This is our material echo in this case, or true level. The little green box is our echo lock window, so that's always going to show up on true level. And then confidence marker is just a depiction of the confidence of the instrument. On your display, you'll also have a confidence value, which will be between 0 and 100. The higher that number is, the happier or more, the instrument is really in tune and knows that that is the true level measurement for you. And then you have some secondary or indirect echoes, which again, we'll talk about a little bit more later on. So talking about how this works and how that echo profile is generated. So whether I've got an ultrasonic or a radar up on top of my tank makes no difference to me. What we're doing here is we're sending out that pulse. Whether that pulse happens to be an ultrasonic sound wave or a radar wave makes no difference. We then get a signal return and we form that echo profile. So once we form that echo profile, we then do some filtering. So if I look back here, I have these little short, quick spikes. Those are not caused by signal return. They might be from ambient, some sort of noise in the background. We filter them out. We apply our TVT, our time varying threshold, and then we have algorithms that work in the background. These algorithms might look at things. Actually, this is covered in the next couple slides, so I'll talk about the algorithms in a moment. We apply our algorithms. We then select our true level, and that's how we output a value for you or display a value for you. So some of those algorithms that I was talking about, there's 3 components that make up the different algorithms that we have. The 3 components are whether the spike or the signal return is the first one to go over the threshold or corresponding second, third, fourth, etc. Then we look at the height or how large that signal return is above our threshold value. So that's kind of like our amplitude, overall size of the spike. And then we look at the area of the overall signal rising above that threshold value. So some of our algorithms might look specifically at just the first echo. We would use that, for example, in a stilling well application. We know our first echo will always be true liquid level. For a more common application, we're going to look at a combination of these 3 criteria, which we call ALF, which is area, largest, and first, based on different criteria, whether we're the first echo, the largest echo, the area above the echo. Every echo gets assigned a score, and the echo with the highest score, the signal with the highest score, is what we consider to be true liquid level. So in this case, this is the second signal return above the threshold, but based on the algorithms, it's the one that we choose to be true liquid level. So this might be, you know, a ladder, a float ball, something causing signal return, and then this is our true liquid level below that. As far as choosing your algorithm, typically just leave it in the default, and if you have any issues or specific questions about an application, you can talk to one of your Gilson sales people, and we can you know, help select the proper algorithm for you. So a little bit more on that time varying threshold that we spoke about earlier. So changes in your process condition, things like foam, steam, agitation, dust, whatever the case might be, can cause that signal return or that echo to go from a high amplitude to a low amplitude. So if you had a fixed threshold value, like many non-contact level devices do, when you have that dusty condition or that foamy condition and that signal drops below that red line, your device goes into echo loss, which is an error mode. And in echo loss, you might hold your previous value, fail high, fail low, however you have that instrument set up. The whole goal of the dynamic threshold is, once again, as the amplitude of that signal changes, my threshold changes with it. So we attempt to avoid going into that echo loss mode. Now, there could still be scenarios where the signal gets to be so low that you can go into echo loss, but it should happen much less often for us because we do have this dynamic threshold value. All right, do we have any questions, Sean?
Yes, we do. Would you mind backing up a slide for this question?
Sure.
So the question is, if the signal never crosses the red line, that threshold line, will this report a loss of signal?
Yes, if your signal never gets above that red threshold, you will be in an echo loss mode.
Then
And
what happens to your output?
you can set it up for one of three scenarios. You can set it up to fail high, which means above 20 milliamps, so typically 22 milliamps. You can fail low, below 4 milliamps, typically 3.6 or 3.8 milliamps, or you can hold your last known good value. And that's all programmable through the instrument.
Thank you. That's all the questions so far.
Okay. So now we're going to talk a little bit about different frequencies and how that relates to different beam angles and you know, where that might be important to you. So all transducers are going to operate at different frequencies, whether that's radar or ultrasonic. Your longer range transducers are going to have a lower frequency. The key to take away from that is lower frequencies have less attenuation, so they're going to perform better in more challenging applications. Things like dusty environments, build up on your transducer or your horn, or dealing with some lighter foaming materials. Short range transducers use a higher frequency, and they're advantageous because you have better accuracy due to the shorter wavelengths, and you might have a shorter blanking distance, or in some case, no blanking distance whatsoever. So kind of the best way that I think about this in my head is, if you are driving in your car, you pull up to a red light, and let's say somebody, you know, a couple cars behind you's paid a lot of money for a stereo system. You're going to hear in your vehicle mostly the bass from their stereo system. And the reason for that is that bass is a lower frequency, so it penetrates better, it attenuates less as it comes in contact with obstructions. So that's kind of the way that I look at lower frequencies versus higher frequencies. The higher frequency might be, you know, the treble or the vocals, which you'll almost never hear when somebody pulls up next to you at a red light. So how does this relate to beam angles within radar? There's three different common families of radar transmitters. I'm going to refer to them as low frequency, medium frequency, and high frequency. And you might see in low frequency anywhere from 6 to 12 gigahertz. Medium frequency, you'll see anywhere from 24 to 28 gigahertz. And high frequency is reserved for 76 to 80 gigahertz. The thing to take away here is, the lower your frequency, the wider your beam angle. So the beam angle on these low frequency radars can get as wide as 28 degrees or so. Your medium frequency is going to pretty much be between 6 and 12 degrees, and then your high frequency, you're typically going to be 4, 6, 8 degree beam angles. The lower frequency is going to be better again for dealing with challenging applications like foaming, lots of condensation, whereas your high frequency is going to be much better for tighter applications where you might have a narrow silo, any sort of solids measurement where we're not at a flat, where we don't have a flat surface. And, we'll talk a little bit more about the details of both of those. One of the things I do always...
Ryan, does a bigger horn?
I'm sorry, Sean?
Ryan, does a bigger horn give me a wider angle?
That's a very good question, Sean. So actually the larger your horn is, the larger the diameter of the horn, the more narrow your beam angle. So it's why when we deal with specifically medium and low frequency radar, we'll typically suggest the largest horn that we can do because it will make our beam angle more narrow.
We have another question asking, does the beam angle affect the distance over which it is effective?
Yes and no, Eric. The only reason the beam angle would have an effect over the distance is if, the location of your transducer, let's say we're up on top of a tank and we're 2 feet off of a sidewall. Well, an 8-degree beam angle might be able to make it all the 20 feet down into your vessel, down to the bottom of your vessel before it has any obstruction from that sidewall. Whereas if we put a 12 or a 16-degree beam angle in that same vessel, we might get a reflection off the sidewall, which will cause errors, and we'll talk about a little bit later on.
Brian, we also have a couple new questions on the time varying threshold. Are you going to get back into that with radar, or do you want to talk about those now while we're not too far past them?
Yeah, we can answer them now.
Okay, so the first question is, why is it called a time varying threshold? Is there a different kind of threshold?
Yeah, so it's called time varying because it's dynamic. It changes with time. So again, as our signal, let me back up here. As our signal changes in amplitude, that threshold value moves with it. So over time, that threshold changes versus what I showed previously. This is a static threshold value. So in an instrument like this, you would program in, or that instrument would select a static threshold value that never changes with time. It would only change if you go into that instrument and manually change that threshold. So if you have an application where you do or don't have foam, when the foam's not there, you're probably great with a dynamic threshold, a static threshold. But when that foam shows up and your signal decreases, well, now you go into echo loss. So that's the difference between the two.
And Mike Snedden asked, what do you consider short range and long range distances?
That's a good question, Mike. For us, our shortest range transducers are going to measure 24 feet or 8 meters, and our longest range radar will go as far as 330 feet. So typically the breakdown there, I would say, would be if you're somewhere between 40 and 60 feet or less, that would be considered short range. You start to cross over above 60 feet and you're going to be into a long range.
So if we had like a 12-degree beam angle and we had a 300-foot range, what's the problem?
Yeah, I mean you're pretty much always going to be reflecting off the sidewall in an application like that. Those long silos might be 10, 20 feet in diameter, and you're never going to make it down to the bottom. So that's what these high frequency radars are used for.
And one more question, David Garcia asked, could you have both a high and a low frequency sensor in the same application and somehow get the average of both in order to get a very precise reading?
You could use say a high frequency radar and a lower frequency ultrasonic in the same application. That's probably something where we'd want to look at your specific application and decide if it makes sense to do that based on what the challenges are of that specific application. But to answer the question, yes, that's something that you could do. So last thing I want to point out on this slide, this medium frequency radar, it's going to be the most common one that you'll see out there. If you're just doing a simple liquid or slurry level measurement using a radar, this is almost certainly the family that you'll be using. I put this slide in here. I mentioned earlier that we would talk a little bit about the price of radar coming down as it relates to ultrasonic over time. So we've recently released a Bluetooth radar family, which is high frequency, 80 gigahertz, works for liquid slurries or solids. And the price point on these types of radars have become very competitive with the ultrasonics. So just something to keep in mind there. Blind units fully configurable via Bluetooth and an app on your phone. 2mm accuracy with 0 blanking distance, and beam angles as low as 4 degrees. So a couple things to keep in mind there. Wanted to talk about this. This is a really good way, again, for me to visualize what the beam angle really means for you. So again, let's look at one of these tanks that might be, a very tall silo, has some sort of solid material in it. This might be 80 or 100 feet tall and maybe only 10 or 12 feet in diameter. As Sean mentioned on some of the questions that y'all have asked, if I've got a radar up there with a 12-degree beam angle, one of those medium frequencies, we're not going to be able to make it all the way down to our solids level before we're reflecting off the sidewall. And when you do that, that causes all sorts of issues with your measurement. You might not get enough signal back, or it'll change the amount of time that it takes that signal to come back, which throws off the accuracy. Whereas if we put a high frequency radar in here, that 4-degree, we can go straight down off of our solid level and come back up. You also see this coming out at an angle. We can aim these high frequency radars, which we'll talk about a little bit later on. And in the past, you might have seen people use a guided wave radar for this. One of the biggest problems with putting guided wave in a solids application is there's a lot of force that acts upon this cable, and we've seen plenty of times where that cable gets snapped or broken off simply by those forces. So how do I kind of relate this? Let's say we were dealing with a low frequency radar, and I'm standing on the top of a staircase, and I wanted to drop a ball off that stair, one of these stairs, and have it bounce back up to me. Low frequency radar would be like standing up there with a beach ball, a very large ball. You drop it off the top stair. It is extremely unlikely that that beach ball is going to bounce off of a single stair, pop back up to me to where I can catch it. More than likely, you're going to hit multiple stairs at once, and that beach ball is going to skip on down the rest of the stairs. Versus a medium frequency radar, that might be like standing up on top of the stairs with a soccer ball or a softball, something smaller in size. You're much more likely to be able to drop it off the top step, have it bounce off a single step, come back up to you. But from time to time, you're still going to hit multiple steps, and it's going to bounce on down the rest of the stairs. Whereas if we're doing a high frequency radar, that'd be like standing up there with a bouncy ball or a golf ball. It would be pretty easy to drop it, have it come hit one stair, come back up to you. So again, that's indicative of the signal return that you're going to get off of your solids measurement down here, and helps explain why the high frequency radar makes the most sense for these types of applications. Okay, things to think about as it relates to installation. So if we were looking at a tank here, and we had these 4 different transducer locations for mounting. This is typically where I would ask people, if I were in a live setting in a group full of people, to tell me which one of these installation points would be best, 1, 2, 3, or 4. And there's typically 2 answers that I get on a regular basis. And so I always point out to people, this is a domed top tank or a parabolic tank, and that actually ends up being part of the answer, which we'll talk about here in a second. So with that, I'll kind of jump into which one makes the most sense. The answer is number 2, and I'll talk about why each of them is good or bad. So for transducer location number 1, this is a question that we've already had answered so far. But if you're too close to the sidewall here, or in this case, this ladder or this fixed obstruction, that's going to cause signal return for us or interference for us, which will affect our level measurement. Now, I will point out that with something like a ladder or any sort of a fixed obstruction inside of a vessel, we could do mapping and we could ignore that fixed obstruction. And I'll have a slide a little bit later on that discusses that. Number 2, this would be our ideal location in this type of a tank. Reason for that is we're about a third of the way in from the sidewall. We don't have any interference from the wall of the tank or the ladder or the fill pipe over here. Number 3, if this were a flat topped tank, number 3 or number 2 would both work, just as well as each other. The reason that I brought up the fact that this is a dome top or a parabolic tank is that dome top can actually act like a satellite dish when you're mounted in the dead center. So what that means is we'll get a signal return from our liquid level, wherever it happens to be down here, and then we'll get a secondary signal return after the signal bounces off the top of the tank, comes back down, and comes back up to the transducer again. And when you have a dome top tank like this, those secondary echoes can actually be larger than your primary echo. And I have a slide that shows that as well. And then number 4, you're doing okay until you start to fill. So this is something that might happen intermittently. It's not a fixed obstruction that's always there. Sometimes you have flow, sometimes you don't. And when you have flow in that pipe, you're going to pick up, that flow, and we're going to tell you, hey, our level's way higher than what it truly is. So you never want to mount in the fill path inside of a tank. And again, just showing you here how number 1 in certain scenarios will work great, but as the liquid level goes down towards the bottom of the tank, you're going to start to have issues with that ladder or that sidewall. So this is just a depiction of a signal return when you're mounted in the dead center of a dome-topped tank. So your primary echo, that might be the amplitude of it, and then that secondary echo that's reflected off that dome top is significantly larger. So in this case, the instrument would want to pick up on that secondary echo. That's why we wouldn't want to mount it in the dead center. If we did mount it in the dead center in an application like this and we noticed our secondary echo was larger, then we would change our algorithm to F, to first, and we would pick up on that first echo profile above the threshold. One other thing to keep in mind, I see this quite regularly on dome top or parabolic tanks, is you want your transducer to be perpendicular with your flat liquid level below it. I know we show it as wavy here, but this should typically be a flat surface. So you want to make sure that your nozzle, or however you're mounting in the top of that tank, allows us to mount the face of this transducer perpendicular. So this would cause issues because we'd reflect at an angle. We wouldn't get enough signal return back up to the instrument. We could go into echo loss. We've talked about a lot of this already on a previous slide, so I'm gonna skip this one. But again, just a pictorial explanation of why it makes more sense to use the high frequency radar in tall silos that have solids inside of them. And this is actually an additional slide that I put in that shows an echo profile between a 25 gigahertz radar and a 78 gigahertz radar in a solid silo here. And you can see on that medium frequency, the 25 gigahertz, we've got a lot of noise, a lot of reflections coming off of different things from inside that vessel. It's got, this is our true liquid level, or excuse me, true solids level, but there are multiple spikes before and after that, at some point the instrument could pick up on one of those, even though it's not true level. Whereas with our 78 gigahertz, we don't have any of those additional reflections coming back, and our true level is a nice clean spike, significantly higher than the threshold. So this just goes to show you how much easier it is when you have that narrow beam in an application like this. Couple things to point out that that might make sense as options, specifically in solids applications. So certain solids can coat or build up on the horn of your radar or your transducer, specifically if it's a high humidity, high moisture environment. So we offer a Teflon cover for a radar transmitter, and what this does for you is Teflon has a very low dielectric, so the radar waves go right through that Teflon face the same way that you or I would look through a window and not see the glass. So this is one way that we can mitigate buildup, as you see in those two pictures. One of the other things that we can do to prevent dust or buildup inside of a radar transmitter is an air purge. So our LR560, one of our solids radars, comes with an air purge built in, and other radar that we offer, we can provide with an air purge kit. So just something to keep in mind if buildup or dust is a big issue for you inside of a horn, and for whatever reason you can't use that Teflon cover. I've linked here an air purge video. Based on time and how many slides we have left, I'm not going to click it. If anyone would like to see that video, send me an email. I'll send you the link, or it's on our website under the LR560 product. There's a video there. Easy aiming flange. I mentioned this earlier. With our solids radars, you can actually aim these radars. So what that means is we have two different flange types that will allow for between 5 and 10 degrees of aiming. So when you get into some of these applications, you don't have a flat surface like we do with liquid level. We're going to have some sort of an angle that solid builds up at, whether it's an angle down or an angle up. And what this allows us to do is aim the radar to where we are getting either the peak of that angle or somewhere along the slope of that angle, depending upon what it is that you're attempting to measure. So this is, again, 5 or 10 degrees of measurement, or excuse me, of aiming capability that you have. Once again, I've linked a video there. I'm not going to click on. That video is also on our website, or send me an email and I will send you the link to that video as well. And this is just a real quick overview of the Siemens portfolio for solids measurement. LR560, LR400 series would be the two most common, and then the Bluetooth radar I mentioned earlier, that's 80 gigahertz. All right, I'll pause real quick. Sean, do we have any additional questions?
Yes, we do. Are there any concerns using a radar in an open air application in regards to government regulations?
Yes, there are. The FCC has guidelines for which you are able to use a radar in an open vessel. It's going to be related to the frequency of that radar and the beam angle of that radar as to whether or not it will meet FCC guidelines. I believe for beam angle, it's 12 degrees or less, and frequency, I would have to get back to you. I believe we can do the 25 gigahertz or the high frequency radar, but I would need to double check on that.
Okay. Another question asks, if a cone or a horn becomes compromised, can just that horn be replaced?
Yes and no. It all depends upon your manufacturer of the radar that you're using, and maybe even the series of the radar that you're using. With Siemens, we do have versions where you can replace just the horn. But I don't want to throw out an answer across the board that's going to be for every radar out there.
All right, and the last question we have so far is, Would a guided wave radar or an ultrasonic be a better choice over standard radar regarding liquids that have a low dielectric constant?
Yeah, so I'm going to assume that standard radar refers to non-contact radar. And yes, if you get below a certain dielectric, I would say anything below 3, we probably want to pay close attention to before we recommend a non-contact radar. And then certainly anything below 1.5, that's really going to be kind of a cutoff point for us. And that's where, if we're dealing with things like hydrocarbons, certain oils, be it vegetable oil or cooking oil, we're going to have very low dielectrics where radar might not be a good option. That radar signal might literally penetrate right through the product in the tank and not see it. So yes, that would be where we would go to an ultrasonic or a guided wave.
Okay, we got a couple more questions coming in. Are there multiple types of coatings on the radar horns, depending on the material being measured?
Yeah, absolutely. Depending upon the dust or the powder that you're measuring, you could easily have different types of coatings. Is that what is being asked, or is this more the coating?
It looks to me like he's asking different materials of construction.
Okay, I see. Yes, standard horns are going to be 316 stainless. We also make horns out of Hastelloy, and then you'll have horns that are made out of some other material. In our case, we do a Teflon encapsulated horn, and then we do a horn that's made entirely out of Kynar. So yes, we do have different options depending upon what the media is or what's off gassing inside of your vessel.
And then we ask, so the mist in a sewage lift station would not interfere with the radar signal?
I would not necessarily say that. I mean, when you say mist, it depends on the amount of water droplets that are in that mist. We should be able to penetrate through it and get a much stronger reflection off liquid level below it. But we'll talk more about condensation and humidity in the coming slides.
Okay, that's all for now.
Okay, so mounting considerations. I'm going to go through these pretty quickly because we only got about 15 minutes left. Just things to point out. We talked earlier about the size of the horn, or in this case, we have rod style radars as well. And again, the smaller the diameter of the horn, the wider your beam angle. So in these cases, got a 6 gigahertz low frequency radar. You can see how wide these beam angles get. We're as high as 28 degrees. You're going to need a really wide tank to be able to mount that in and not have any sort of issues from sidewall. Needs to be said that if you're mounting into a nozzle of any sort, that you want the horn of your radar or your ultrasonic transducer to extend out 1/4 to 1/2 inch below the lip of that nozzle. When you're doing a rod style radar, that is from the point where the diameter or the rod tapers down. So want to make sure that we have that extend out of the nozzle. Again, same thing with the medium frequency radar. The only thing to show here is as that horn gets larger, these beam angles become much more narrow, and we'll get down to 6 to 8 degrees in a medium frequency radar. Now, one thing from the nozzle that's extremely critical is just because the nozzle from the outside looks like it's only 4 or 6 inches in length, that doesn't mean that it does not extend inside the tank. So you always want to measure that nozzle from inside the tank, so you know exactly how long it is, and you can make sure your horn or your transducer is extending down below that nozzle. Other thing to point out here on this slide is when we're doing these rod style antennas, the beam angle or the shape of that beam is as you see here, where it's wider right up at the top, and then you have more of the teardrop shape below that, compared to your horned radars, where it comes out in a conical shape like you see here, or a teardrop shape. All right, so now we'll start to talk about application challenges and really get into foam, mist, condensation, some of the questions that have come up. So again, as it relates to speed of sound, I bring this up because our speed of sound changes with temperature, and our speed of sound changes as it goes through different atmospheres. So I've said a few times with ultrasonic, it's speed of sound through air. The takeaway there is if your vapor space above your liquid level is air, then we're great with ultrasonic. If it is something other than air, be it, off-gassing from sodium hypochlorite, sulfuric acid, whatever the case might be, that's going to affect the speed of sound through that particular media, which we show here, which is going to have an impact on the accuracy of your level measurement. It's not that you won't make a measurement, it's that your accuracy will be affected. Here's some different changing process conditions that we've talked about, or we're going to talk about. So we'll have foam, which we'll spend a lot of time on, agitation inside of a tank or a vessel, and then condensation or buildup on a product. So one of the most common things that I see in Florida is foam. All over the place in lift station applications. See them plenty of times in process plants where we're doing any sort of a reaction. So we're going to talk about the 3 different types of foam. We're going to talk about different frequencies of radar and ultrasonic and how each would fare in a foamy application. So the first kind of foam that I'm going to talk about is a real thick, dense foam. I think of this as when I pour beer into a cup, and you get a nice thick foam, head layer on top of that beer. That would be like our dense foam. So when we're using a low frequency radar, this is what our echo profile might look like. We get a pretty good signal reflection off of that foam. Nice high amplitude. One of the things to keep in mind though is that reflection is coming off the top of the foam layer, not the liquid level below it. So we get a good clean signal, but we're not telling you where your liquid level is at. We're telling you where the top of your foam's at. In a lift station, not typically an issue. Foam's only, a few, 2, 3, 4, 6 inches, and it's not too big of a deal if we're off by that amount in a lift station application. Ultrasonic. We actually get a very nice clean signal reflection off of ultrasonic. Again, coming off the top of that foam layer. And then medium frequency radar, also good clean signal return, and there would be no issues here. So when we're dealing with dense, thick foam, we're going to see that change in dielectric or density off the top of the foam layer, and it shouldn't cause us any real issues. Now, if we go to a light foam, so when I think of a light foam, I think of something that would be like if you're doing a load of laundry, the kind of soap scum you might get on the top of that load of laundry in the washing machine. So if I start with my medium frequency radar, I get a very slight signal return. We may or may not be able to do anything with this. That's probably going to be a little bit tough to deal with because the amplitude just isn't very high. So it's going to depend on other things in our application. When I do ultrasonic, I get a decent signal return here. That's probably a signal that I'd be able to work with. And in both of these cases, we're actually penetrating the foam here and giving you a true liquid level measurement. And then for my low frequency radar, I actually get a very similar signal return as I got when I had dense foam. So for our lighter foam, the low frequency radar is the best choice. And that makes sense because it's better at penetrating anything. It attenuates less, so it can penetrate that foam better, reflect off the liquid level below it. So low frequency makes the most sense for light foam. Now where we really get into the head scratcher and we don't have a great non-contact answer is when we're dealing with medium foam. So I would describe medium foam more similar to like if you give your kids a bubble bath and you've got some airy foam bubbles in that bubble bath. I do medium frequency radar, I don't get a signal return. Ultrasonic, same thing, no discernible signal return. And low frequency radar, it's the same thing. There's no real signal return. So what would our answer be for something like this? This is ideal for a submersible pressure transducer or a contacting technology. So all that said, the key takeaway here is there's no magic bullet for foam. What you need to take into account with your foam is what's the makeup of my foam, the consistency of my foam, and am I okay measuring the top of my foam level, or do I actually need to know the liquid level below it? So these are some different installation challenges that you'll see that are all fixed obstructions. Again, we can map all these out, anything that's fixed. Now, an agitator blade, it's not necessarily fixed from the standpoint of it's constantly moving, but if we have it in a stationary state, we would be able to map that out as well. So how does that work for us? We have something called auto false echo suppression. So the same thing that we talked about earlier, you have the pulse, you get your signal return, you're forming that echo profile, we do our filtering, apply our TVT profile, apply our echo algorithms, but which one of these should we pick up on, the fill pipe or liquid level below it? Well, if we run a auto false echo suppression or a mapping, we can actually map out that fill pipe. So you want to run your auto false echo suppression when liquid level is as low as possible in the tank, so we can see any obstructions that might be in there. And what we would actually do is set the range value from the face of the transducer, how far down in the tank we want to run it, and then that becomes our suppression range that we learn. So we would reapply our TVT filter, and it would contour above this fixed obstruction. So that's how mapping works to ignore any sort of fixed obstructions inside of a tank. Again, just some different challenges that we'll see in applications, and why the 6 gigahertz makes more sense to use than the medium or the high frequency. All things that we've talked about already. Some more application challenges that I just want to point out. Anytime you start getting temperature gradients or high temperature, you're going to want to look at radar. Again, that's because speed of sound through air is affected by temperature. Radar is not affected by temperature or by pressure. So if we're dealing with high temperature, changes in pressure, or vacuum, these are radar applications. If we're dealing with vapors in the headspace, dust, or foam, specifically low density or medium density foam, again, straightforward radar applications. All right, Sean, I know we're getting short on time. You want me to answer any other questions now or wait until the end?
Why don't you wait till the end?
Okay. So just real quick, advantages and disadvantages of both. I mean, we've talked about a lot of these specifically already, but again, advantages of ultrasonic, just across the board, well proven, been around a very long time, non-contacting, can do liquid slurries, or in some cases might be able to do some solids. Self-cleaning transducer face for many manufacturers. That's because the face of this transducer actually vibrates as we're sending that signal out. And disadvantages are going to be sensitive to vapors instead of air, foam, and then pressure and temperature ranges or gradients. Radar, you're going to see a lot of the same advantages. Non-contacting, the big differences are we don't care if there's vapor or dust in there, unaffected by changes in temperature or pressure, and we can do all three of the solids, liquids, or slurries with no issues. And we'll talk about this a little bit later when we look at individual applications, but we can penetrate through plastic tanks. Disadvantage, can still be sensitive to foam, really heavy condensate, and the FCC guidelines that somebody asked about earlier. Differences between ultrasonic and compact Bluetooth radar. I'll just point out the radar here. Really good for remote battery operations. Your range can be as high as 30 meters, which is longer than we'll go with ultrasonics. And you can measure through plastic tanks, great with vapors in your headspace, can work in a vacuum or carbon dioxide environments. So now the last 15 or so slides, I just run real quick through a bunch of applications and talk about which would make more sense between ultrasonic and radar. So the first thing you might see is a pumping station. Um, for me, if I'm dealing with a lift station or a pumping station, I'm going to want to go with an ultrasonic that has a narrow beam angle. So, we might be able to get as low as 6-degree beam angles in these types of applications. And typically inside a lift station, you're going to have fairly dense foam or a grease layer. And your big concerns are just not a ton of space inside the station. So really good for ultrasonic, or if you wanted to use a high frequency radar with a narrow beam angle, that's a possibility as well, just depending on how much condensation, moisture, humidity you have inside the station. We talked about this one already, so I'm not going to spend a ton of time here, but bar screens or mechanical screens doing the differential across. It's really nice for an ultrasonic because we have a dual channel transmitter that'll talk to 2 transducers and do that math or that differential for you. It can even do an average across, depending upon what it is that you want to see. And we give you relay outputs to do any sort of control function based off of some differential level. Haven't talked much about open channels so far, but to touch on this real quickly, there's 3 big reasons that ultrasonic make more sense than radar for open channel. First off, the majority of ultrasonics nowadays are going to have open channel flow tables built into the transmitter itself. So you can go in and choose the type of flume or weir that you have, and it will convert the level measurement to a flow rate for you based on the change in head height just before your flume or your weir. But ultrasonic is faster in response, has a quicker response time than radar. And in many cases with these open channels, you're constantly changing that head height as your flow rate changes. So you want something that responds very rapidly. If we compare an accuracy spec between an ultrasonic and a radar, our best ultrasonic has a 1 millimeter accuracy spec, which is best in class for any ultrasonic and can beat any radar that we offer. And again, with some of these larger open channel applications, a 1/4 inch or 1/2 inch difference in head height or in level might equal a 500,000 or 1 million gallons per day of flow. So we want to be as accurate as possible. And then the last thing is we have shorter ranges for our ultrasonics than we do for our radar. And because of that, you have more resolution in your range that you're measuring. And most of these open channel applications are only measuring a few feet of range. So we want as much resolution as we can possibly get. If we look at sludge collection in a gravity thickener or chemical dosing, these are typically pretty straightforward, simple applications for ultrasonic, where we're not dealing with too many challenges as it relates to foam or anything else that we've talked about. So from an economical standpoint and an ease of use standpoint, ultrasonic probably makes the most sense in these applications. Within water, wastewater, when you start to deal with digesters, this is probably the one application that is a slam dunk radar application. There's always large amounts of foam in digesters. We're talking a few feet of foam, and they're typically very large tanks, wide in diameter. So we're able to use a low frequency radar, get it mounted a few feet off the sidewall via some sort of bracketry, and it really helps us to deal with the foam inside the digester. Chemical storage, be it in a water, wastewater plant or an industrial plant, can really go either way. The reason that I say that is if you have a well-ventilated tank that is getting any sort of off-gassing coming out of the tank and keeping it to where the vapor space inside of the tank is air, then ultrasonic can be a good technology for you. But if we have a tank that either doesn't have ventilation, the ventilation doesn't work well, and we're going to have vapors off-gassing and building up inside the vessel, that's when we would want to go to a radar for those chemical storage applications. If you're dealing with any sort of a granular application, be it in a water plant, a lime tank, or any sort of a power plant that might have some type of a pebbled lime or dehydrated lime, that's always going to be a radar application. and you're going to want to use a high frequency radar there. Again, you're typically dealing with very tall, very narrow silos, so we want that really tight beam angle and that aiming capability. In the cement industry, there's a multitude of applications within the cement industry that we could talk about, but the key takeaway here is many of them, and this is solid silos in general, is they're very tall, very narrow, and lots and lots of dust. So again, high frequency radar, narrow beam angle, that's going to be what you want to use for these types of vessels. Really want to talk about this one. It's something that has gained popularity and gained traction over the last couple of years. Since radar transmitters are looking for a change in dielectric, depending upon the plastic material of my tank, I can mount a radar outside of the tank, and we can penetrate directly through that plastic material. This only works with plastic, and it only works with certain types of plastic that have a low enough dielectric. But if you're dealing with a plastic tank, you want to be able to mount something outside the tank, either for compatibility purposes with what's inside the tank, or you don't want to give up any head space due to blanking distance. This is a good solution. So keep in mind that we can only do that with radar. If you're dealing with short or medium range solids, again, high frequency radar is probably the best way to go for all the reasons we talked about today. Narrow beam angle, going to be able to aim it to deal with this angle here, and quick response time. If you're doing a volume inside of any type of a tanker or truck, we can use the 80 gigahertz Bluetooth radar because it has no blanking distance. So once again, you're not giving up any ullage or space inside of your tank. Doesn't really matter what's inside of the vessel, nor does it matter what the process conditions are in there. Radar could be a good application for you. And then we talk a little bit about condensation dripping. With ultrasonic or radar, there's different things that we could do here. With ultrasonic, we have, again, that self-cleaning face that is there to help try to get that condensation to vibrate off the face of the transducer. We can also spray the face with Rain-X and put this at a very slight angle, maybe a degree or two, and allow the condensation to bead off. But as you can see in this photo here, we sprayed this unit with condensation, allowed it to freeze on there, and then we could still get a good level measurement. Plastic pellets or wood shavings. I just put this on here because it's a little bit different from granulars, still a solids application, and again, just a great application for the high frequency radars. And then here's a bunch of different applications that you might see in, say, a chemical plant or some type of an industrial plant, be it power or whatever the case might be, all of which would be, slam dunk radar applications. You would never want to try an ultrasonic in any of these. Solvents, going to be lots of vapors. Same thing with your resins and, polyether liquids, petrol, hot water with steam condensation, high temperature, pressure gradients. So just some applications to look at that should always be done by radar. And then these are all applications that you would want to do with your high frequency radar, be it cement, hot mix asphalt, pellets, any of these powder type applications, all going to be your high frequency radar applications. All right, so this is my last slide here. Again, just shows some different buildup, whether it's condensation, some water droplets that froze on there, grease, different types of things on the face of these high frequency radars, and that we can penetrate a lot of different scenarios that you might traditionally think are not a good non-contacting level application. So bring your applications to us. We'd be happy to look at it and make a recommendation for you based on your specific challenges. So sorry I'm about 10 minutes over, but we'll open it up now and answer any questions for those that have stayed on.
Okay, Ryan, so you talked about running the auto false echo suppression in an agitated vessel. Dan, whoops, just lost my question. Dan Vale had asked, is it better to apply that false echo suppression with the agitator on or off?
It can be done either way, Dan. You know, if it's going to be running during normal operation, which, you know, most agitators or all agitators will be, then you know, you should probably run that auto false echo while the agitator is on, so we can get a best idea of what process conditions are going to be like while we're trying to make a measurement.
We have a question on your TVT curves that you were showing. How do you get those TVT curves?
Oh, great question. The TVT curve is a standard on all of our Siemens non-contact level products. You don't have to do anything for it. It's constantly working for you in the background. And yeah, nothing you have to do. It's always there and working for you. Anything else, John?
Yes, but how do you see it if you want to see it?
Oh, how do you see the TVT curve? You go into an echo profile. So depending upon which transmitter you're dealing with, you can access an echo profile either through the push buttons or a handheld, or you can hook up to it with a any heart-based software, and you can look at an echo profile that way. Anytime you're looking at an echo profile, that TVT curve will be on there.
Okay, for water-based applications without foam, do you recommend ultrasonic or radar?
I would recommend ultrasonic for all nearly all water-based applications without foam, unless, you know, it happened to be a high temperature or pressurized situation. But traditionally for me, a water-based application is going to be an ultrasonic application.
Okay, and another customer asked, can you touch briefly on the software that is available for Siemens product setup, these meters and transducers, and to get the echo profiles, map out obstructions, etc.
Sure. Siemens has a product called PDM. That's P as in Papa, D as in Delta, M as in Mary. And PDM is a heart-based software. It allows you to talk to any of our heart-based instruments, and you can go in through PDM. You can access echo profiles. You can do a full programming of your instrument from anywhere in that loop. You can save configuration files. So there's a lot of power in PDM. And David, if you want to talk offline, I'll be happy to answer more questions for you. And then there's also other heart-based softwares that can be used. There's things like Pactware. Basically, on all these heart-based softwares, you just need access to the device driver or the DTM file for that instrument. You download it into your library, and then you'll be able to communicate with that device via a heart to USB or heart to serial modem.
And last, Frank Scoron asked, will the webinar be available to view again? I'm glad you asked that, Frank, because the whole reason we're duplicating this webinar is we forgot to record it the first time. And we've done a whole bunch of these so far, and they're all available to view off of our website, gilsoneng.com.
Yeah, and if anyone would like a specific link to the webinar, just shoot me an email and we'll get that to you as well.
And another question just came in. Using a heart loop, can you have multiple radars on the same loop, reducing the PLC inputs?
I believe the answer to that question is going to be no, if I'm understanding it properly. So each radar is going to have its own loop. You know, the 4 to 20 signal coming off of it is going to go into an individual input card on your PLC, and that loop is going to have the 4 to 20 signal, the heart signal, and it's going to be what's powering your instrument.
All right, looks like that wraps it up for us then.
All right. I certainly appreciate everybody's time this morning. If anybody would like PDH hours or needs any additional information from us, please let me know. Thanks for your time.